there. Nice to see everybody. My name is Sean Lally, and I'm going to talk to you today about some physics demonstrations. This is actually part one. This is a re-recording because yesterday when the workshop first happened, I maybe forgot to record. So I hope this works fine, and let's get started. Let me get my screen sharing happening. And that should do the trick. Okay, so this part one is actually part one of the full workshop. The workshop has to do with half of it has to do with physics demonstrations. I'm calling it physics demos galore, and the other half is all about things that you can build by yourself or with your physics students. And here we go. So again, this is called Physics Demos Galore. I want to thank Susan Zawacki from Pittsburgh, Pennsylvania, for inviting me to PittCon this year. I'm sorry I can't be there in Georgia myself, but I'm presenting this from Baltimore, Maryland on June. Wow, what date is it? June the 7th, 2022. Again, my name is Sean Lally. I teach at Genesee School and Towson University. I also have a class over at Johns Hopkins in engineering that I teach during these summers. So this has an unofficial title of 60-ish demos in 70-ish minutes. Let me tell you a little bit about demonstrations. Demonstrations are the first thing that really sort of captured my imagination when it came to physics. If you are of the right age, and I'm starting to approach a group that's going to be a smaller and smaller group. But if you're of the right age, you might have seen Julius Sumner Miller on public television. He was the first physicist I had ever really heard about when I was, oh gosh, I guess I was a teenager. And it was the first time I had ever seen the physics demonstrations being done. And they really captured my imagination. I thought they were fantastic. And the thing I loved most about them and him was that he didn't exactly explain what was going on. He gave you, I mean, he explained some, but he gave you things to think about. Later, of course, I'd seen Mr. Wizard, and then met Paul Hewitt, who's definitely sort of a true legend of physics teaching. Any of you who are familiar with teaching physics, especially conceptual physics, definitely know all about Paul Hewitt. So these three guys were incredibly inspirational to me, as well as Jack Horkheimer for teaching astronomy. If you've ever seen Stargazer before, or if you're old enough, you will have seen it when it was called Star Hustler. He was pretty amazing. Very influential to my astronomy teaching. James Randi, I should mention as well, who is also very influential to my my skeptical approach to teaching science, especially as it goes up against pseudoscience. So I dedicate this to all of them, and thank you for being here. A few general things to think about. I've been teaching for quite some time, definitely a few decades. And when I first started my teaching career, I have to admit, I think I did what a lot of people do, and I taught the way that I had been taught. And of course, I'd had basically a lot of university professors as my most recent role models, and I don't think they were very good role models. So I hopefully have better strategies by now. I started out teaching in public schools. I taught in rural schools and more urban schools. I've taught in a lot of private schools, universities, high schools, colleges, middle schools, community colleges, all of museums. And I'm not saying that to brag. I'm not even saying that to give me my words more, more gravitas, nothing like that. I've had all sorts of students, rich students, poor students, and I think they all want and they all need good teaching. Where I've been for the last few years has been at a school that focuses on students who have dyslexia or dysgraphia or any kind of related learning issue. They're generally college-bound students, and they are incredibly bright and wonderful students, but they're struggling. Some of them we call twice exceptional or thrice exceptional if they have dysgraphia or ADHD, or maybe they've got issues with calculations, issues with writing, all sorts of things. So as I've tried, a person way smarter than me once said this, but I teach students, not physics. And try and keep that in mind. I'm not teaching physics, I'm teaching students. I think they actually said, I'm not teaching chemistry, I'm teaching students, but still, I try and think of it that way. I'm, excuse me. Obviously, you want them to understand it. You want to challenge them, but you got to remember what it is like to be a kid, who has a whole lot of other things on their mind. So with that in mind, let's have at it. So the first part of this is going to have to do with things in mechanics. And I'm going to start off with kind of a very simple inertia demonstration. So this is one that I've been doing for quite a few years. It just involves a couple of billiard balls and a coin on top of them, usually a dollar coin or a 50-cent piece, something like that. A coin that's got a little bit of heft to it. Doesn't really matter, but it's a little more impressive. It's kind of a bar trick. I have to admit, my dad showed me this one. And normally you might do it on a pool table. But the idea here is I just sort of set up a faux pool table. Right here, I've got a piece of foam core. And let's just play this short video. You hit one billiard ball with another, and you try and knock the coin off. And as long as you keep both balls on the table, no pop shots, nothing like that, it is very, very difficult to get that coin out of a circle. Usually I do this on a piece of cloth, maybe a blanket or something like that I can draw a circle, rough circle onto with chalk. And that's probably about 3 or 4 times the diameter of the ball. Let me show you this one more time. There's our coin. We're going to hit it out of frame. There you go. The coin basically drops straight down. A nice little demonstration of inertia. Here's some other things that you may have possibly seen before. These are sort of classics. These are not mine, although I've done these before. Didn't have time to set these up and do it. They're nice inertia demonstrations where you can actually knock the tray out with your hand, or you can use a broom, sort of a broom vertically and using it as sort of a lever principle with your feet on the bottom of the bristles and just whack it that way. Another couple of really good demonstrations here. This one on the left is a real favorite of mine. I did not set it up to show it to you, and it is a bit of a challenge. You have 2 wine glasses, and there's a pole. Usually I'd use a broomstick and put little finishing nails on either side. And basically the nails rest on the glasses. Make sure the glasses have a good amount of liquid in them. Wine glasses work well. They make it really dramatic. Support the wine glasses between 2 desks or something like that. In this image, which is a borrowed image, it doesn't show you, but they basically should be at about a little bit lower than that, because you want to strike this with a metal pole. I usually use a pole from a ring stand and hit it swiftly, and it will break this. It will impart a whole lot of force to the center and virtually no forces to the glasses, so they should remain standing. And it's a wonderful demonstration. Practice it first. Over here, you've got a Jenga-like demonstration also for inertia. Okay, switching gears a little bit, I want to talk about one way to introduce torque or moment. By the way, I didn't. This was in the slide information that was on an earlier slide, but this is actually really important. I think when I used to do demonstrations, I used to do it all myself. And now have your students do it without a doubt. Get them in there. If your slides, I always share my notes with students. I share my slides with them. If they are internally used, that is, if only they're going to be used by your students, then I like to have pictures of my students actually in the slides, and I tend to update them all the time. Even if I'm using a similar lesson from year to year, I'm going to change out the slides with students so they basically remember, or they see somebody from last year. It's just another way to basically keep them focused and saying, hey, I know that kid. So that kind of thing. So over here, I've got a student who's holding a kilogram mass, and I'll say, okay, you get somebody who maybe they say they're kind of strong. You say, hold this for me. They can do it, not an issue at all. But then have them hold it at a distance of 1 meter away. And if you just hold a meter stick, I'm using a little using a little lever fulcrum clip right here with the kilogram weight hanging from it. It is incredibly difficult to do it. It imparts a really big torque to your wrist. Most students can't do that very easily. So it really gives you a good way to start talking about torque and moment. And then similarly, take a broom. I actually don't like this particular broom for this purpose because it is actually a little more balanced near the geometric center. But anyway, so take a broom that has a heavier bristle side and balance it at its center of mass. Then ask the students, where is which end is heavier? Is it the left end with the bristles? Is it the right end that's longer with more pull? Ask them which end is heavier. Of course, most of them will say that they are equal. And this is really worth coming back to later when you get into the guts of center of mass and rotational equilibrium. If you're feeling really ambitious, take a wooden broom and, take a wooden broom and cut it actually at the CM, drill out a little hole on each side and put a dowel rod in there, a little short chunk of dowel rod, and that way you can't actually break it apart and measure the weight differences. So that's really worth doing. Oh, I love center of mass. I really do. It's one of my most favorite topics to talk about because it's so incredibly visual, even when the center of mass itself is not. So I've got a few things. There's some stuff here. I made this out of some scrap metal, a little bit of welding. Most people aren't going to do that, but you can make it out of wood. You can barely see this one back here. There's a little wood block and some wire, a couple of wooden beads. I think these came from Michael's Crafts. Here I've got a toy that came from an art museum, balancing bird. This is great right here. I don't even know if you can quite tell what's going on here. This is a nail that's pounded into a block of wood, and it is supporting what looks to be about 14 other nails. This is kind of a classic demo. And with this, you actually have got a little drawing here that you can kind of see. You start off with one nail. You do this all horizontally, laying on a desk. Start off with one nail and then alternate nails perpendicular with the nail head on the opposite side of the central nail, and basically put them perpendicularly, then have another nail, the final nail, on top to kind of lock them in, lift it up by the center of mass and balance it on that nail. It balances beautifully. The CM is somewhere here within the basic shaft of this nail, and it's it's a really great and simple demo. And if you get it right, well, you nailed it. You're welcome. Okay, next. This is a classic right here. You got a fork and a spoon. Don't use a spork, please. It won't work that well. You want to use a fork and a spoon. And that you can barely see is a toothpick right here. I have it balanced on I think it's a soda bottle, like a root beer bottle, but it works on a glass too. It's a great dinner demonstration. But the thing I like about it is to take like an aim and flame, a lighter, and just light both sides of the wooden toothpick. And the nice thing is students, of course, will expect it to fall apart, but it won't. And actually what will happen is the flame will go out once it reaches the glass and the metal, because they're better thermal conductors. Let's see what else. We got a Weeble toy back here. The Weebles wobble, but they don't fall down. That's a little Cookie Monster. We got a mock-up of Leaning Tower of Pisa. Oh, another toy of Balancing Bird. All good center of mass demonstrations. Another one, Ernest the Balancing Bear, right here. He actually travels on string, and you can run him across the room, have a student help you with that. If you're feeling ambitious, then get a windshield wiper motor. I usually find stuff like that on eBay. Get one, you can run it with 12 volts or less, put a little variac in there, and not a variac, but just a potentiometer, and you can actually have it move back and forth very slowly, and attach a string to one side of the motor and attach the other side somewhere in your room. And basically you can have Ernest go back and forth for hours. I hope that makes sense to you. It's a little bit challenging to do it, but mostly it involves finding a good motor that will allow you to actually attach a string to it. And you want an oscillating motor. You don't want something that goes round and round. You want literally, you can make it work, of course, but it's easier if it's something that just goes back and forth. Here we got a classic, the wine bottle support. This is easy to make in a wood shop. Just take a piece of wood, put an off-center hole right here, flatten out one side. You can see just by looking at it, nothing special about it. You probably don't want to do this with wine in your classroom. That may be frowned upon by, well, everybody except for the students. But do it with a 2-liter bottle of soda and it works perfectly well. It'll work great. You can buy these too, but it's just as easy to make. Okay, it's not just as easy to make, but it's reasonably easy to make. Make friends with your shop, with your art department, with your tech department. They can help you amazingly. Or, put a shop in yourself, in your own classroom. In the latter part of the second part of the talk, with the building stuff, I actually talk about how to outfit a small shop in your classroom. Some more CM stuff. We've got the classic bouncing bird over here, where the CM is below the fingertip, and this is also just thrown together from from some scrap metal that I had laying around in a shop. Okay, now here is a great purchase for your room, a block and tackle. Boy, oh boy, I used to think that I was going to have to buy a block and tackle, a block and tackle from, I don't know, I thought I was going to have to find an old one, like an old sailboat block and tackle. And that was my quest for years, but no, you can just find a small one on Amazon or eBay or whoever, and just get one based on the capacity. So this is a small capacity one that I think probably supports. I'm looking at it right now in my room, and I'd say it just probably is capable of supporting, maybe 50 kilograms or so. But this one, which you can't see, of course, you'll see it, I think, in the next slide, is capable of supporting hundreds of pounds, hundreds of kilograms, I really should have said. And this way you can have a student lift up another student in the room. Now, they can't go all the way up to the ceiling. This is a bosun's chair right here. I highly recommend that. So the block and tackle itself is on the order of $20 to $30. The bosun's chair is cheaper, although you can actually use a vinyl swing from a deconstructed, a swing set. Here it is again. I've got a student. There's the block and tackle right there. And Allie happens to be sitting in the bosun's chair, and she has actually pulled herself up off the ground. So, and you can see that it actually doesn't go up that high because of the cords on the bosun's chair. I didn't want it to be dangerous, although I could shorten these if I wanted to, but I didn't want them to actually be able to go up to the ceiling just because, safety. And this way, the worst thing that can happen here is falling. You're only going to fall, just a meter and a half. Not such a big deal. What you can't quite see in this is that there is also in the ceiling. I'll talk more about how to use ceiling in your room, but there's also another eye hook that I have attached to the exposed girders, metal girders in my room. And there's another very high capacity eye hook that can hold up to 500 pounds or something. And I attach a locking, not exactly a carabiner, although you can use a carabiner as long as it locks. So I've got basically a locking, I can't remember exactly what they're called, but it's basically a kind of, it's a chain link basically, and it has a thumb screw on it. So you can use that to attach your bosun's chair if you want, and basically you make a human pendulum. And this is great when you want to talk about the mass independence. You have students take turns swinging in it, while other students in the class will measure the time of the period, have them do 5 oscillations or so, 3 to 5 oscillations, and determine the actual period. And they'll see that it doesn't depend at all on the mass of the student. It doesn't depend on how far back they go, at least not much. Obviously, it does depend on how far back they go a little bit. It's not totally independent of the amplitude or so, but the actual difference is small. As most of you probably know, even if you take it to almost 90 degrees, the difference in period is only about 12 or 13%. It's not a huge difference. If you want to read more about that, go to the Wikipedia page on the pendulum, and you'll get into the infinite series that shows you the full expression, which is great. I love that. What else can you do? Also, if you have students swap out on the bosun's chair when you're doing a pendulum demonstration, you'll see that it will actually, there'll be some experimental differences, obviously, but the biggest differences are going to come with height differences, not so much weight differences. You'll find that the students who are taller versus shorter are going to have different locations of their center of mass. So that's going to effectively change the length of this nearly simple pendulum. Okay, totally changing gears here. Let's talk about trusses. I like teaching students how to analyze trusses when we get into engineering, at least in my engineering class. And one nice thing to do, this is pretty simple to make, just with some scraps of wood. You can use rulers, wooden rulers as well. But make a triangle here and then make a parallelogram. Push down on this, and as long as these bolts are a little bit loose, you'll see that this thing will collapse immediately. You push on it, it collapses. So right away, this tells you that this is problematic. This, on the other hand, is very, very, very strong. And as long as you don't go past your compressive strength, etc., and the tensile strength. Also, it helps students visualize why these are in compression and why this is in tension. You can do it with popsicle sticks too. I've seen people use popsicle sticks and a piece of string. You know, that is totally fine. The reason I don't do that is because nobody builds bridges like that. Oh my gosh, I'm totally changing gears again. Slow-mo video. My school did the greatest thing 3 years ago, and we banned phones in the school. And that is awesome. I mean, students still find a way to get distracted, but at least it's not with phones anymore. And yeah, so we basically ban phones. We allow them to bring phones, but they have to keep them turned off throughout the day. They can only turn them on at the end of the day, especially if they're, if they've got to get picked up or have to send a message to the, the family. If they have to send messages any other time, they've got to go to the office for that, or just use phones in our classrooms. Okay, so why do I mention phones? Because everybody's phones now, probably if it's a smartphone, can do slow-mo video. Really great. You notice that the student over here is doing a bowling ball drop, and that is actually a little, it's not a super ball, I can't remember what it was. I think it's a sad ball, actually, if you've seen those before. It's not really bouncing. The bowling ball's bouncing way better than that guy. Maybe it's a marble. It's hard to see. I chose poorly for this because of the background contrast, but you can definitely see that they land at the same time. It's nice to see that on slow-mo video, especially because you can do video analysis of it, which I'll talk about in a moment. So bowling ball, classic demonstration, but you want to be able to watch it over and over and over again. And so doing slow-mo video of it is great. Usually what I'll do is I'll have a student slow-mo it for me, or I'll take the video myself if I'm actually watching a student do it. And then I'll quickly email that video to myself, or I'll just use the Google Drive app on my phone and just share it with myself, so I can then show it on the big screen and play it frame by frame. Sometimes immediately import it into video analysis from Vernier software, all sorts of things you can do. Now this is a ballistics cart, which most of you have seen before, I'm sure, but doing this in slow-mo is worthwhile. Also notice that I've got basically a train tunnel right here. There's the ball leaving and landing in the cart. Oh, bouncing. Oh, let's watch that again. It's kind of funny. You can't see this on the board back here, but I tend to make my slide sets pretty explicit. So if there's going to be a part in the slides that will say, what are we going to do now? It's kind of funny that I've gone so far away from chalk and talk, which is what I did for years. I prided myself on being able to walk into any classroom and talk about anything, with nothing more than a piece of chalk. And I thought I was awesome for doing that. And yeah, when I think about it now, it almost makes me shudder a little bit. Sure, I can talk and talk. I don't know how long I've been talking now, a long time, but it doesn't make students all that interested, despite how interesting I might think I'm being in the moment. Okay, anyway, but so I'll do is here's a demonstration. What will happen here? Then there's discuss with some questions behind it. Partly I do that because, well, I think it makes sense, but I really had to start doing it when I was teaching at the school where I do primary work now, and it's because the students need a lot of scaffolding. But here's a secret. All of your students need scaffolding. They really do. Okay, let's watch this one more time. If you want, you can always play it in slow-mo. You've got options over here, but you don't need to. This was recorded in slow-mo. There's the ball landing in the ballistics cart. Now, why do we do that? Well, we do it so we can repeat it, but also I like to do it because when you import it into Vernier's video analysis or Logger Pro, they both do the same thing, but Logger Pro is more expansive. Video analysis is primarily for your students who have Chromebooks, just like graphical analysis is an app for Chromebooks now. All of this is Vernier stuff. I'm not a paid spokesman for them, but their stuff does not cost much, and it is truly worth every cent. And plus, it's always site licensed. Okay. This is what I love about it. That is the X and Y. That's the X and Y coordinates of the ball's position, right? Look at that. The red dots tell you immediately that it's going horizontally at a constant speed, more or less. You can fit a, you can easily fit a line to that. It'll give you the horizontal speed. And the blue gives you this beautiful parabola that basically just proves that the ball has some acceleration component in the vertical direction. It is amazing. There, I've just added some info right here. It's the vertical motion of the ball, the horizontal motion of the ball. It's good to have this stuff in your slide sets too, because if you have students who miss, well, geez whiz, you can't, I think we have a tendency to sometimes get mad at our students when they miss, and that's usually not any fault of their own, and things happen in life. So you just try and make it easy for them to catch up. And, spoiler is it's easier for you too. Well, this speaks for itself. This is one I generally do on my own, because if it fails, I want to be only able to blame myself. I want to point out a couple of things here with the tablecloth pull. I'm using not a tablecloth, but rather a very low friction pillowcase, and only no stitching to get in the way. It's a very old pillowcase. I think it might be from my childhood. Yeah, it's kind of embarrassing. It's also covered up with photochemical stains. Also, this is usually filled with food here, and I've got liquids. That increases the drama, but the truth is it actually also increases the inertia, which makes the demonstration easier to do. I tend to drag this demonstration out a lot. The longer I drag it out, the more annoying it gets for students, but they also start to get super excited about it, and they're like, just do it. Yes, I will do it, but I usually have a good 5-minute buildup where I'm reading from Newton's Principia, and I'm consulting it as though it's a user's manual. It's a little bit of acting, but it's meant to be fun, and it always works. I also find that students really do want to film this because they're kind of silently hoping it's going to fail. So I will let them film this, and I usually find if I have to do it 3 times a day or 4 times a day, honestly, they will have shot it and they will have Snapchatted it or posted it somewhere, and immediately, other students will see it by the end of the day. So, and that's awesome, except if the demonstration fails, and that's happened before too, where other students came and they told me later, like, "Wow, didn't go so well this morning, did it?" Got to remind them, physics never fails, man. Sometimes you just fail to meet the requirements of physics. Watch this GIF. I like this. It's a little hard to tell what's going on here at first. A couple of things. First of all, I've got a little chunk of I-beam in my room, which is one of those founded at a construction site sort of things, and was never not going to pick that up. So now I've got two not equal dynamics carts. That one's about 3 times heavier than this one. And then there's spring loaded. This guy's going to push the spring out. Okay, so this is not surprising whatsoever. You have done Newton's third law demonstration before, I'm sure. Here's what's surprising. It's balanced like a lever, and it remains balanced, even though this guy's way heavier. It doesn't change at all. Why? Well, it doesn't change at all because there's no change in the momentum. The net change, the total change in momentum is 0. There's no external forces acting on it here. So there's no reason for the whole thing to upset its rotational equilibrium. So it's a simple demonstration that shows a lot. And doing it in slow-mo is also kind of cool. Oh, here's a variation on that done with people and skateboards.
Go ahead.
2 skateboards. Light student, heavier student on the left. It's a very simple demonstration. Have kids do it. Have them predict what happens if one pushes the other. Things like that. You got to have them predict things, because you'll be surprised that their predictions are often, they betray some misconceptions, and you've got then the golden opportunity to address those misconceptions. Showing this one more time.
Go ahead.
because I like it. There you are. I mentioned earlier how to make use of your ceiling. So here's my block and tackle right here. Again, that was probably a $30 purchase. There's a couple of eye bolts there. I'm looking at them right now. There's lots of different ways to attach things to your ceilings. I've worked in all sorts of different schools, and I've been in schools where they tell you, no, you can't attach things to your walls, can't attach things to your ceilings. You know what I usually end up doing in that case? I usually say, I don't say anything. I just do it. You do it now and ask for forgiveness later. The truth is, I don't do things like that just to be a problem for facilities or for administrators. I do it because it really, truly increases the educational experience. And if they can't see that, then they are in the wrong business. So it is important that, in fact, you can even ask your facilities folks to install some load-bearing eye hooks for you. Make sure they get them into beams or into joists or whatever you have. Most likely, there's going to be some metal girders. And I don't want to say don't take no for an answer, but tell them it's important. And if, don't have them do a dozen of them unless they're really, really wanting something to do, but at least a couple, one or two gets you started pretty well. I also have some these are spooled up electrical cords right here. These ones are kind of cheap and they don't always survive that well, but it's nice to have cords from the ceiling that you can drop cords that are actually plugged in the ceiling, and then it's just basically a nice shop thing that makes your floors a lot cleaner when it comes to electrical cords. You can see right over here, I've got these things in the ceiling. They were there when I got to the room. Over here I've just got kind of a Calder type, an Alexander Calder type mobile. I like mobiles a lot. I talk more about mobiles in the building things, the building stuff in physics part of the workshop, which is the second half. If you only have a drop ceiling in your room, we'll get the drop ceiling clips. They're usually pretty strong, and I wouldn't hang from them. They're not designed for that, but you can hang a bowling ball on a chain if you needed to. The tensions on that's only going to be, I don't know, 20 pounds or so. It's not really that big of a deal. So you can definitely do that. Test it. Just don't allow kids to hang from it, and don't leave the chain hanging there within students' reach. Most of the time, I always have positive expectations for kids, but the truth is sometimes your students just can't resist something cool. And honestly, neither can I. Having a rope swing in your room, maybe not the best idea, Also, just a mobile hanging front. I have an artist friend who made that for me. I thought it was really pretty cool. I talk more about mobiles later. A few other things that you'll see here that I address. Just having wall clocks, usually different time zones, because at some point you will be talking about time, and it's worthwhile to talk about the weirdness of time. And just having time zones, that's a great place to set up a good conversation. Okay, a lot of you, this is one thing that doesn't often come up in a first year physics class, but if you talk about the pergristochrone problem, the path of least time, a tautochrone curve. This one is cut. I cut this one from styrofoam. I actually just used a small, oh gosh, what kind of saw is that? Small jigsaw, a hand jigsaw. I did it that way. Make sure you wear goggles and a face mask, because styrofoam, will get all over the place. So it's easy to do. It only takes a few minutes. But this is from a 4x8 piece of styrofoam. I have two of them. You'll see why in a moment. And all I did was I took a bicycle wheel and basically, or no, maybe it was a lid from a garbage can. In any case, it was round. And I did your classic attach a piece of a pen to it, or a marker in this case, and just move it out, and that will trace the curve. You have to experiment around to find the right size, of course, but basically you want something with a diameter that's about the height of the board, maybe the width of the board, I should have said. The height of the board in this case. Okay, so when you're done, it's going to look like the one in back. This is the other one. This is going to just be a nice right angle plane right here. Now, attached to these, I think you can sort of see, is Hot Wheels track. The Hot Wheels track is glued onto the styrofoam. Gluing things on styrofoam is not easy. So you want to use stuff that you can find in a hardware store, Home Depot or whatever, Lowe's, that's called Great Stuff. It's that foam in a can. It's the expansive foam. Be careful, wear rubber gloves, because that stuff is messy. And you basically want to kind of put it on the actual edge when you're done cutting. And and then you're going to attach the track there. You will need to tape the track down and kind of squeeze out all of the great stuff, the foam. So have it attached there, tape the track down, and when you're done, it's going to be kind of it'll be permanent basically. And then it'll look something like that. No, why do we do that? Well, we do that because we want to at some point teach about the shortest distance between 2 points is not necessarily a straight line, you know? So, or at least the shortest time between 2 points is not necessarily a straight line. So you can do this with Hot Wheels cars. I tend to do it with that. I use Hot Wheels track because I had some, but you can also use, Hot Wheels cars. You can also use steel spheres. And in fact, in this short video, this is a slow-mo video, but I'm actually using steel spheres here. You can hear the rumble. There's the one down the cycloid, and then there's the other one. Put something at the end. Now you can see it in real time, but honestly, I'd rather watch it in slow-mo because it's cooler. Okay. Got a few other demonstrations to talk about with inertia, etc. Plastic eggs. These are Easter egg type things. They're hollow and they come apart. This one's empty. It stops. You spin it and it stops. This one, I put some water inside. Stop it. Doesn't stop. Great way to just get into some applications of inertia. You can talk about raw eggs versus hard-boiled eggs, etc. But literally, it's very easy to tell. This one stops. I didn't do this so well, but it stops. The other one, the stuff inside is still moving. Keeps going. This is using a poi ball. And is it showing up?
Yeah.
Even though it's dark? So it's illuminated ball in a dark room. Okay. Go ahead. I'm going to let go of this in a few seconds over here at the 3 o'clock position. And there you see it basically goes straight up. But let's watch this in slow-mo. It's a little bit easier to see this in slow-mo. And it just takes a little more time. I notice every time I do this demonstration, it always seems like, there you go. That's beautifully easy to see there. Oh, hold on, let's go back a little bit. Watch the path. That's really nice. You have probably done a spinning bucket of water before when you talk about the velocity equals the square root of RG. These are fine. I find these to be a little more dramatic. The spinning platform, spinning plate. That's an IKEA plate over here. That's just a little wooden coaster. And I just put holes in them, attach strings, and that's it. Works really well to spin around. You want to put a glass on here filled with water. Well, maybe not a glass. I used to put a beaker on there and well, let's just say I don't have that beaker anymore. So now I usually do it with a, something that's a little bit more hardy. You can do it with a mason jar or something, but plastic cup of water is your safest thing. But make sure it's a clear cup. I actually think it's worthwhile so that students can literally see that there is stuff inside there. And again, shoot some video of it. Starting it's easy, stopping it a little bit challenging. What do we have here? This is shelf bracket metal directly from Lowe's or Home Depot. Big steel ball. Nothing really special about this other than you can talk about dropping it from one side versus dropping it from the other side. Fairly simple.
Go ahead.
And of course, talk about the effects of friction, etc. Oh my gosh, this is one of the more amazing things that I couldn't have done when I first started teaching. Using motion detectors and, well, I take that back. I guess motion detectors have been around for, quite a while, but they're not as cheap as they've been the last 10 or 15 years. So I also want to point out that I put virtually no effort into this particular demonstration. I just set it up and walked away. So there's a bowling ball on a chain. I took a bowling ball, drilled a hole into it, and put an eye hook. Can you see that in back? Let me back up here a little bit. Oops. There you go. Look at that curve being generated in real time. You'll see it up close, surely, but that, my friends, That is a beautiful sinusoidal curve. That is amazing. It's a 5-second data collection. I think it collects 20 pieces of data, 20 points per second. There's my motion detector there on a little lab stand, or actually my little chunk of I-beam, connected to a mini LabQuest over here, and that goes over to my PC. And then there's the data. I honestly, yeah, I guess I really kind of wear my nerddom on my sleeve, but when I see that as data, from just a pendulum swinging back and forth, oh my gosh, it's beautiful. You can do it with a mass on a spring too. If you want to do something a little fancier with like the classic toy on a spring. I say classic as though all of you have one of these around. Doesn't everybody have a frog hanging from a spring? So anyway, but you can just basically take a decent spring. Any spring with a low K will work pretty well, and hang a mass on it. Tape an index card to the bottom, and then put your motion detector underneath of it, and you'll generate beautiful, beautiful data. Index card or a piece of foam core works really well, and if it's foam core, you can reuse it, of course. Here's a classic. And this is one that students really are continually surprised by. These staggered pendulums. There are better ones online. I just kind of had this one laying around. I thought it was worth mentioning. So starting how they are, they all eventually get back in sync. You can look up the mathematics of this. It's, it's not all that crazy. But it is worth doing. You can have, again, if this is something you don't want to build yourself, or you can purchase these. They're relatively inexpensive with smaller pendulum bobs. You can definitely purchase one for probably about $20, but you can, if you want to have a student build one, it might be a good project too. All righty, shifting gears here, talking a little bit about fluids, pressure, Bernoulli principle, and such. This is simple. 2 cans, empty cans of soda. You can do it with baseballs if you want. I find the soda cans work a little bit better. Hanging from strings. There's a little ring stand up there. Blow between them. Most people will think that they will go apart. You could also take a little air jet. Like if you happen to have a small compressor, you can direct air between them. That works fine. And I stole that totally from Julius Sumner Miller. That was one of the first things I remember him doing. Actually, I will mention a brief Julius Sumner Miller story. I wrote him a fan letter when I was younger, and I wrote him a fan letter. And well, this isn't really funny. I don't even know why I'm laughing, but his wife wrote me back because he had actually just passed away about 6 months earlier. And yeah, but she was so sweet and kind, and she sent me one of his personal books, and it really, really touched me. And I've never forgotten that. I still have that book actually behind me on my shelf. So she sent me one of his demonstration books. So I never had a chance to meet him or chat with him. I lost out by a few months. Actually, he had passed away literally months earlier. Oh, classic toy right here. These are things you can find if you do orders from Oriental Trading, or you can just find it as a little eBay find. Arbor Scientific probably also has it. Another classic right here. This one's weird. I like this one. This is the first one I think I ever thought about. As an index card made into a little table, but blow under it. Most students will probably think it'll flip, and it actually makes it more stable. The air pressure on top holds it down. Let me show you that one more time. Very simple. Here you go. Watch the increasing angle. Think gotta thank my little boy for videoing that for me. Okay, now we have got a handful of other moving stream of air Bernoulli type demonstrations. Toy, balloon, copter. Attached here is like $1, $2 thing. Let go. First of all, it sounds awesome and it's fun, and it demonstrates the third law, Newton's third law, as well as the differential of pressure. Whirligigs, these are great. You find them in the Science Museum. It's a silly little thing, but these things have been around far longer than planes have been, actually. So I kind of like the historical. They were a curiosity, a toy, but actually they got people to start thinking about how things could fly too. Now this one is going to take a little bit of explaining. So curve. Okay, so right here, this is my curveball demonstration. That is a mailing tube. This is, I cut a little chunk of it off here, and right here, that is a piece of sandpaper that's glued to this end of the mailing tube, and there happens to be a styrofoam ball. And basically, just by whipping it horizontally, you can show how a curveball works. Oops, sorry about that. Let's play that one again. Mailing tube, curveball, sandpaper, styrofoam ball. Hard to see because I had the camera didn't capture the whole frame, but basically I'm throwing it horizontally, whipping it horizontally, and I move the ball in one direction and it curves in the complete opposite direction. Some toys shown here. This is a cross section of a wing from a remote control helicopter, propellers, fan blades, anything to show that things that are meant to fly have a curvature to them, or an angle, whatever, 7-degree angle or so, if we're talking about things that are flying. Okay, let's get into wave, sound, and optics a little bit. Harmonics lab. This is an expense that's worth it. A classic harmonics lab. So if you, I get this stuff from Pasco, but you can get it from any other place. I'll show you how this works. Basically, let me talk you through it. We got a sine wave generator right here and a string oscillator. They are a little bit pricey, but it's so worth it because that's an n=1 harmonic. And then usually I have this as a discovery type lab where students find as many harmonics as they can with a meter and a half of elastic string here. Then you can generally find the fundamental pretty easily, and maybe 20 or 30 harmonics. I use it as demonstrations. I use it with a strobe light. I tried to show this, but it didn't video so well. So it's definitely worth seeing up close. And a strobe light, a digital strobe light, is an investment you really do want to make at some point. So this is just an n=1 harmonic, but you can get n=2, 3, 4, and they can very quickly see the linear nature of the harmonics, the frequency being linearly proportional to the harmonic number. The other thing that's cool about this is when students calculate the speed, they measure the wavelength, they calculate the speed, frequency times wavelength, they find that it's constant. And that is almost always shocking to students if they think about it. They're like, they usually thought, if I have them write a hypothesis for this, they'll usually think that the speed will go up with higher frequencies, but not a chance. In fact, the speed remains constant, of course, right? So this type of lab or demonstration is really useful to show that the speed is constant regardless of the harmonic number. You can change the weight. If I have 5 lab groups doing this lab, I'll have each of them do a different weight. And then at the end, they'll compare the fundamental frequency to the weight. And you can see that the greater the weight, the greater the fundamental frequency. And you can even have a chance at seeing that it's a square root relationship for velocity versus tension. Once again, you can sort of see an n=2 harmonic going on in here, but strobe lights highly recommended. Some Doppler effect stuff for you. This is about as simple as it gets. This is a tuning fork on a string. Oops. That's very simple, right? Works great. Again, with a resonating cavity. Here's a buzzer on a string. Your little corrugated plastic tube, easy to find. Why do I like it? N equals 1 harmonic, N equals 2 harmonic, N equals 3 harmonic, N equals 3, and N equals 4. A couple of other things that are worth remarking about. I do like to teach about the physics of music because my other life is as a semi-professional musician. And so with that, the fundamental is, of course, your N equals 1 harmonic, and the N equals 2 harmonic is 1 octave above that. The mathematics of tubes, as you probably know, is exactly the same as the mathematics of strings that are fixed on both ends. The mathematics of tubes open on both ends is the same as strings fixed on both ends. So the second harmonic is 1 octave above the first harmonic. The third harmonic is actually 1.5 times the first, or the second, sorry, and that gives it a musical interval of a fifth. So so it's like bum bum bum. You know, if you know, gosh, what is that piece? Is it also thus spoke Zarathustra? I can't remember. I'm sorry. It's in 2001. You know the movie, so you probably know the piece. Anyway, so you can hear not only do the harmonics get higher in pitch, but if you have a student who's a musician, or if you're a musician, you can see it starts out N equals 1, N equals 2 is an octave, N equals 3 is a fifth above the octave, N equals 4 is an octave above N equals 2, and it's 2 octaves above N equals 1. And if this means nothing to you, well then, fret not, physics friends. Maybe you don't have to get into too much of the guts, but I think you do want to learn and talk about octaves, if nothing else. One more time. N equals 2, N equals 3. You know what? This is also worth mentioning. I've had students who are really good musicians, and they noticed. I had a couple students with perfect pitch, and they said, "No, that's flat. The faster you spin it, the more flat it becomes because the tube is getting a little bit longer, right? So of course it's going to have a longer wavelength, therefore a lower frequency, and be a little bit flat." Chladni plates. Goodness, if you've never done Chladni plates before, my gosh, are they beautiful. It's my most favorite thing to ever show. Thin aluminum plates, supported at the center of mass. I always do the square plate. It's the best one, but round plates are fine. Violin shaped plates have a nice vertical symmetry, so they are good as well, but square plates are the most important ones to do. I'll show you some brief video of this that I shot a few years ago. So, there's a whole lot going on here. Of course, the plates are resonating. The mathematics is fairly complicated here. I believe it uses Bessel functions. There's a really good book called The Physics of Musical Instruments. I honestly can't remember the author off the top of my head, but in that book, they will show you the images associated with Chladni plates, and you can predict what the frequencies will be based on the density of the plate and the dimensions. It's a lot of work. It's not that big of a deal if you just want to show it, however, and it's worth seeing because students then see that not only do strings undergo harmonics, but so do plates, and so do drum heads, and so do, anything can undergo a harmonic. If it's uniform, it's easy to see them more or less. I do a wire loop as well. I didn't show that here, but wire loops are nice. If you have them supported at the bottom, they will oscillate beautifully and give you a whole series of harmonics. But not only that, they will, not only that, but they will oscillate a lot like a glass does. If you are trying to shatter glass with a wine glass with sound, it will oscillate. There's some really great clips available on YouTube where people go for the professional clips, like the scientists, the physicists who are doing it, not just some yahoo trying to break a glass with sound. Literally find the ones people are doing it in a lab setting because they're better. They do it with high speed cameras and you'll see the glass oscillate. It's awesome. I don't do that as a demo anymore because it used to hurt student ears and my own. So anyway, Chladni plates, highly recommended. And that's just that's sand. I can't remember what kind of sand that is. Actually, it's sort of a weird kind of sand, but it's not just beach sand. But anyway, you can get it with the plates. Oh my gosh, Rubens tube is wonderful. I'm going to show you this video clip here first. So Rubens tube is basically a small tube. Here's one. This one's actually not complete, but I've got the one I'm using here is longer. It's probably about 1.5 meters long. And it's basically got a nozzle on one end, and the other end, there's usually a piece of, I tend to use a piece of thick plastic and duct tape it over. It has to be a flexible membrane, and you put a speaker on one end and drive it. This is the kind of demonstration that takes some setup, but I think is super worth it. Now, this is a slow-mo video, but it's definitely going to allow you to see how the flame height changes sinusoidally. Now, why that is pretty subtle. When you drive it with a sound wave, you're driving it with a longitudinal wave, and that will cause the molecule separation and density and pressure to vary sinusoidally. You will then get higher and lower flames that are also sinusoidal. Slow-mo is kicked in there. There you go. Look at that. That's a sine wave. If you're feeling crazy, you can even do things like determine the speed of sound in propane based on the the actual dimensions of the flames. It is really pretty beautiful to do. It takes some time. It's worth it. And also, you often have to make your own Rubens tube. I found you can find them, but the one I use, I actually made myself. It is kind of amazing to see. Just show you a few more seconds of this. There you go. Easy to see the sinusoidal nature. There's some other Rubens tube video, but this is actually not as good, so I'm not going to show it to you. It's not as good. I can say that because it's actually also mine, but I didn't like it as much. Okay, speed of sound. If you have access to sulfur hexafluoride, and really, who doesn't? Actually, you probably don't. But you can watch the clips. These are clips of me breathing in sulfur hexafluoride. Oops, sorry, let me show you that again.
This is sulfur hexafluoride, take 2. You can probably tell extremely low frequency from my voice. This is ridiculous.
You get the idea. Speed of sound in sulfur hexafluoride is about 134 meters per second compared to like 340 something meters per second in air. So it's not, it's on the order of 1/3. So you get a much lower frequency. It's like breathing in helium, but more dangerous. So you have to be sure to get it out of your body when you're done breathing it in. Cough to get it out. Laser shows. 100 meteors is a bust, guys. So laser show. This is a simple laser show with a couple of rotating mirrors that you can basically, have in and out of phase. It's really simple to do. and it shows you Lissajous patterns. You can do this with a pendulum also, like a coupled pendulum, and sand or ink or whatever. I know many of you have seen that before. Here's the DIY version right here, where you got a laser hitting a couple of mirrors. That's a mirror with a little wooden dowel chunk in there and a flat piece of flat round mirror glued to it. And then you can just basically vary the two speeds. All right, so the next big topic here is all about electricity and magnetism. And that is where I'm actually going to end, because the next part, the part 2 of this, goes into the E&M demonstrations pretty well. So that's what is really coming up next. And in this next part, you'll see a bunch of demonstrations with electrostatics and circuits and a whole ton of stuff. So thanks so much for watching so far. And, at the end of this, there's ways to get in touch with me if you want. You can email me at Sean P. Lally. That's SEANP as in physics, Lally, LALLY, Sean P. Lally at gmail.com. Happy to answer your questions. And I think that's it. So that's the end of part 1. Thanks very much.